Okay, so the last thing we need to talk about is the divergence operator, and the Laplace-Beltrami operator. So let's talk about the divergence of a vector field. The divergence of a vector field is going to be defined as essentially the Lie derivative of the Riemannian volume form with respect to that vector field. Okay. So remember, the Lie derivative of a tensor field is essentially we look at the Lie derivative of a tensor field in with respect to a vector field x is you look at the flow induced by that vector field, okay, and then you essentially take your tensor field and pull back along the flow so that you take the tensor field, evaluate it at a certain moment of the flow. So like the tensor field evaluated at a certain moment of the flow, let's say phi x of t, and then you pull that back to the original location by the pullback of the flow map, which is a local diffeomorphism for small times t. Okay, so this gives you basically a tensor which belongs to the tensor, basically it belongs to the it's a tensor located basically in the tensor product of the tangent spaces of the manifold at a fixed point, because when you pull it back, you're basically keeping the tensor fixed at a fixed point on the manifold, and so that allows you to take the time derivative. Okay, so it's basically the time derivative of the pullback of the tensor field evaluated at the flow phi t of x, the pullback of that by phi t of by the map phi t of x. So that looks algebraically like phi t x star of um, omega g, where omega g is the Riemannian volume form evaluated at phi t of x. Okay, and then you take the time derivative at t equals 0, and taking that time derivative will give you the Lie derivative of the tensor field. So in particular, the Lie derivative of the Riemannian volume form, that Lie derivative in the direction of a vector field x is precisely going to be the divergence of the vector field x scaled by the Riemannian volume form. So essentially, you take that derivative, you get a new top form. That top form is going to equal some function, some function from the manifold into the real numbers, multiplied by the Riemannian volume form. That function, that coefficient function of the top form, when you take the Lie derivative of the volume element, that coefficient function is defined as the divergence of the vector field with which you're taking the Lie derivative with respect to. Okay. Now, an important point here is that there's an alternative definition, which is essentially you take the exterior. You take the exterior derivative of the interior derivative of the Riemannian volume form, the interior derivative with respect to the vector field x. Okay, so it looks like d of ix of omega g, where omega g is the Riemannian volume form. Okay, so you take the interior derivative with respect to the vector field x of the Riemannian volume form. Then you take the exterior derivative of that new n minus one form, and it gives you another top form. And the coefficient function of that top form is the divergence of the vector field. Okay. Now this can also be calculated in local coordinates, and essentially, yeah. So in local coordinates, the divergence of the vector field of the divergence of a vector field is going to be given by 1 over the square root of the determinant of the metric in those local coordinates, multiplied by partial I, the summation over I of partial I of the ith component of the vector field times the square root of the determinant of the metric. Okay, so if we call the square root of the determinant of the metric in these local coordinates, if we just call this square root of g, let's say, then in local coordinates, the divergence of a vector field is 1 over square root of g partial I of xi square root of g in parentheses. So xi square root of g is in parentheses, and then we sum over I. So essentially, if g is constant, right, if g does not vary with respect to any of these partial derivatives, any of these partial i's, then we just recover the traditional form of the divergence, which is the sum of the partial derivatives of the with respect to the ith coordinate of the ith component of the vector field. Okay, but here we have the ith component of the vector field being scaled by the square root of g, where g is the determinant of the metric in these local coordinates. And so we scale that, scale the ith component by the square root of g, then take the partial ith derivative, so with respect to the ith coordinate, sum over I, and then finally multiply by 1 over the square root of g, where g is the determinant of the metric. Okay, so you can calculate this in local coordinates. It's a good exercise to do so. You essentially use the definition that I just gave you, um, and then essentially, how would you do this calculation? Oh yeah, because you basically express the Riemannian volume form explicitly in terms of the local coordinates. And remember, it's just going to be partial I wedge, or partial 1 wedge, partial 2 dot 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 wedge, partial n, or equivalently, it's going to be, if you actually take a coordinate chart, it's going to be the square root of g times dx1 wedge, dx2 wedge, dot 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 wedge, dxn. So if you take the coordinate form of the Riemannian volume form, and then you do the calculation of taking the interior derivative with respect to a vector field x, and then taking the exterior derivative of that n minus 1 form, you're going to get a top form whose coefficient with respect to the Riemannian volume form is precisely in coordinates the expression that I just mentioned to you. Okay, so now let's talk about the Laplace-Beltrami operator. So the Laplacian of a function f is defined on a manifold, compactly supported function manifold is defined as the negative divergence of the gradient of f. Okay, so the negative divergence of the gradient of f. Oh yeah, one more thing I forgot to mention about the divergence. So this Lie derivative interpretation of the divergence. So the divergence of a vector field f is the Lie derivative in the direction x of the Riemannian volume form omega g, or at least the coefficient of that resulting top form. So this can be thought of as the rate of change of the volume element um, under the flow of the vector field. Okay, so locally how the vector fields flow distorts the volume of the space. Okay, and that's in line with our traditional geometric notion of divergence in Rn. Okay, and so moving forwards, we have this notion of the Laplacian, which is the negative divergence of the gradient of f. Okay, that's the Laplacian of f. Now you can express the Laplacian in local coordinates. I'm not going, well, actually I will mention it just because I have it right here. So in local coordinates, you have that the Laplacian of f is equal to the negative divergence of g superscript I superscript j partial subscript I of f partial subscript j. Okay. So just the gradient of f, right? The gradient of f, we take the one form df, and then we essentially apply the sharp map, so that raises the index of the coefficients of the one form df to give us the vector field gradient of f. And the coefficients of gradient of f are given by the ith coefficient is like g superscript alpha superscript I partial subscript alpha of f. Okay, and where g with superscripts is the inverse of the metric tensor given by the 0 to, so the inverse of the metric. Okay, so we take the divergence of this resulting vector field grad f, and then it just becomes negative 1 over square root of g, where again g is the determinant of the metric tensor in these local coordinates. So, okay, Laplacian of f is equal to negative 1 over the square root of g, partial I, open parentheses, square root of g times g superscript I superscript j, partial subscript j of f, close parentheses. Okay, so um, so yeah, that's the coordinate expression for the Laplace-Beltrami operator. Now, some important things to mention. So we have Green's formula and we have the divergence theorem. Okay, so the divergence theorem holds in Riemannian manifolds. Let me just state it for you. So here, the divergence theorem: let X be a smooth vector field with compact support on a Riemannian manifold M, comma G. Then the divergence of X integrated over the manifold M against the Riemannian volume element is equal to 0. Okay, and this essentially follows from a really important proof, which uses the essentially the product rule for the divergence. Okay, so the proof of this result of the divergence theorem is going to use a key lemma, which is that for any smooth vector field and for any smooth function f, so for any smooth vector field x and for any smooth function f, one has that the divergence of f times x is equal to f divergence of x plus g of grad f comma x. So that means basically this is the product rule for the divergence. So we have divergence of f x is equal to f times the divergence of x plus the inner product with respect to g of the gradient of f with the vector field x. Okay, and so and this just you can calculate this in local coordinates to prove this, just using the definition of the gradient of f. Um, so So the point is, we can use this fact to prove the divergence theorem over a full manifold, and it allows us to invoke a partition of unity. Okay, so the idea is we have the divergence theorem holding true for functions for vector fields whose coefficient functions are fully supported on a single coordinate chart. All the coefficient functions are supported on a single coordinate chart, and then because of this corollary that basically the product rule for the divergence, we can take basically we get a result about the partitions of unity, which is that if rho alpha is a partition of unity subordinate to some atlas, then the summation over alpha of rho alpha divergence of x is equal to basically the summation over alpha of the divergence of rho alpha times x minus the inner product of the gradient of the sum over alpha of the rho alphas, inner product with f. But the sum over alphas of the rho alphas is a constant. Let me just show you what I'm looking at here. Yeah, so we have this divergence theorem, and you can see here that the summation, if we just insert a partition of unity here, because of this product rule for the divergence theorem here at the center of the screen, we have that essentially the summation over alpha of rho alpha divergence of x is equal to the summation over alpha of the divergence rho alpha x. Okay, so take a partition of unity and sum over that partition of unity of the divergence of x, it's equal to the summation of the divergence of the rho alphas scaled by the x. So basically this partition of unity, as long as you keep the sum, it's going to commute with the divergence, which is very powerful. Okay, so that allows us to actually extend the divergence theorem to just any smooth vector field with compact support on a Riemannian manifold. Okay, all right, so now we define the Laplace-Beltrami operator as the negative divergence of the gradient field of f. Okay, so now um, we will just mention that with this Laplace-Beltrami operator, it's a very important operator, according to this author, Zuoqin Wang, Professor Zuoqin Wang, who wrote these lecture notes. Um, he says that it is the most important differential operator on Riemannian manifolds. It plays an essential role in the analysis of Riemannian manifolds. Okay, so with this Laplace-Beltrami operator, we can get Green's formula. Okay, so the key thing is, if we have Green's formula, if f and h are smooth functions on M, and either f or h is compactly supported, then the integral over M of f Laplacian h dv is equal to the integral over m of the inner product with respect to g of the gradient of f and the gradient of h dv, which is equal to the integral over m of h times the Laplacian of f dv. Okay, so in particular, if we view this integral as an inner product of f and h, or we equip the manifold, the manifold, or at least the compactly supported functions on the manifold with an inner product. So we take the vector space of compactly supported functions on the manifold, we equip it with an inner product with respect to this Riemannian volume form. Okay, namely the inner product of two functions is just going to be the integral, like let's say f and g. The inner product of f and g is integral of f dagger g against the Riemannian volume form over the manifold. Okay, so that's our inner product, and now we can complete this inner product with respect to the L2 norm, and this gives us a set of integrable functions. And so it turns out that if we have functions which are compactly supported, then it turns out that the the this Laplace-Beltrami operator, this Laplacian, is a symmetric operator with respect to that inner product. Okay, so name the result here. So you can see the inner product of f Laplacian h is equal to the inner product, or sorry, the integral of h Laplacian f, which is equal to the integral of the inner product of gradient f with gradient h. Okay, and and then you can see this written out in the inner product format. So you can see that the L2 inner product of f Laplacian h is equal to the inner product of Laplacian f with h again. And since these functions f and h are assumed to be compactly supported, that means dense subset of this L2 space of integrable functions. And so we see that if M is compact, then this Laplace-Beltrami operator is a densely defined symmetric operator on L2 of Mg. Okay, if M is compact. Okay, and so all right, so now we can generalize these Green's formulas to compact Riemannian manifolds with boundary. So that means let M be an m-dimensional smooth manifold with boundary, which is also a compact subset of an still m-dimensional Riemannian manifold N, and whose the Riemannian structure on M coincides with the Riemannian structure on N. Okay, so we kind of have an ambient manifold which is of the same dimension as M, and its Riemannian structure coincides with M. Okay. Then we can define, on the boundary of M, we can define an outward normal vector field nu. Okay, so an outward normal vector field nu, and an induced Riemannian metric. Okay, on the boundary of M, the induced Riemannian metric is going to give us a volume density. Remember, this induced Riemannian metric is just going to be the pullback under the inclusion map of the boundary. Okay, so you can include the boundary; it's going to be a submanifold. You're going to pull back the metric on N on this larger manifold of the same dimension, pull back that metric onto the boundary, and this will give you a metric on the boundary of M on this lower dimensional, like m minus one dimensional submanifold of N. Of course, it's the boundary of M. And so we get pulling back the metric on N via the inclusion map, we get an induced Riemannian metric on the boundary, and that comes with a volume density, dA. Okay? And then using that, we can generalize the divergence and Green's theorems. Okay, so for the divergence theorem, we get the integral over M of let me say, for any smooth vector field X on M and any smooth functions F and H on M, we have the divergence theorem, which is that the integral over M of the divergence of X dV is equal to the integral over partial M of G of X comma nu dA. Okay, so in words, that's saying the integral over the manifold of the divergence of the vector field X with respect to the Riemannian volume form is equal to the integral over the boundary of the manifold of the inner product with respect to G of the vector field X with the outer normal vector field nu to the boundary, dA, where dA is the induced Riemannian volume form on the submanifold partial M of the larger manifold N. Okay, and then we have the Green's formula. So Green's formula is given by the integral over M of f Laplacian h dv is equal to the integral over M of g of the gradient of f, comma, gradient of h dv minus the integral over the boundary of M, g of nu, comma, gradient h, um, and then scaled by the function f dA. All right, so in words, Green's formula states that the integral over the manifold of the function f times the Laplacian of the function h, so negative divergence of grad h, with respect to the Riemannian volume form, is equal to the integral over the manifold of the inner product with respect to G of the gradient field of f and the gradient field of h. Okay, so that inner product of those two vector fields integrated against the Riemannian volume form over the manifold minus the integral over the boundary of the manifold of G. So the inner product, again, the inner product with respect to the metric G of the vector fields nu, which is the outer normal vector field to the boundary, outer unit normal vector field. Yeah, I'm assuming it's an outer unit normal vector field. It should be. And then so we're taking the inner product of G of the outer unit normal vector field nu with the gradient of h, and then we're scaling this by f dA. Okay, so theorem in Green's theorem, and I'll just show it to you here. So the top one is the divergence theorem, the bottom is the Green's theorem. Okay, so we have the left-hand sides here, and then the right-hand sides. Okay, hopefully, okay, I think this may be the right angle. Okay, so just take a moment, pause the video, take a look at those. And then the last thing I wanted to mention is this important proposition, which I don't fully understand yet. Still learning this one. But look at this proposition here. A diffeomorphism psi from M to N is an isometry between MGM and NGN if and only if it commutes with the Laplace-Beltrami operators, i.e. the pullback under psi of the Laplacian of f with respect to n is equal to the Laplacian with respect to m of the pullback of f under psi for every f within the smooth functions on n. Okay, so basically, a function is an isometry if and only if it commutes with the Beltrami-Laplace operators. So that's really interesting. Okay, since we're looking on camera now, let me just go ahead and show you the formulas that we just talked about. Okay, so you can just see them. Okay, so yeah, so right. So I guess the first formula is this co-area formula. We talked about this in the previous video, but here is the foliation of leaves gamma t. You can see this integral here. So this is we scale f by grad u, integrate over the Riemannian volume form over m, and we get this, basically this dvg breaks up into a 1 over grad u, a norm grad u dt times dst. Okay, so this is a nice co-area formula. And then we're going to show you the divergence formula. So the divergence in coordinates. The original definition of the divergence is here. Okay, so you can see those definitions of the divergence of a vector field. Okay. All right, go ahead and pause the video if you want to look at that for longer. And then we have the divergence of the vector field in coordinates. Okay. And then right here, so we get the divergence of the vector field in coordinates here. And then also we get the product rule for the divergence. That's this line right here. Here's the product rule for the divergence. Okay. All right. And then we have this Laplace-Beltrami operator. Okay. It's the Laplacian. And then now we have the generalized. Okay, this is a key idea. If you have compactly supported functions, that's critical, and M is a smooth Riemannian manifold. Okay, without boundary, compact without boundary. Then this Laplacian is a symmetric operator, densely defined symmetric operator. But remember, we need M to be a compact without boundary. If M is instead satisfies these conditions, compact Riemannian manifold with boundary, okay, you can look at these conditions for M to be a compact Riemannian manifold with boundary, and I explained them a minute ago. Then we get these wonderful and beautiful theorems, this divergence theorem and this Green's formula. Okay. Okay. Yeah. All right. Have a nice day.